Okay, so we have seen three adaptive algorithms so far. The first one was ADA-GRAD, which had this problem of rapidly killing the learning rate, which was solved by RMSprop by using an exponentially averaged history. But still it had the problem of dependency on the initial learning rate. So then we saw ADA delta, which got rid of this initial learning rate and made the effective learning rate a ratio of two histories, right? Now, continuing in our algorithms continuing our journey towards the algorithms with adaptive learning rates, we'll now look at ADAM, which expands to adaptive moments. And the intuition here is that do everything that RMSprop does, right, to solve the decay problem of ADA-GRAD, which is to use an exponentially weighted history. In addition, use a cumulative history of the gradients as you used in a kind of momentum-based algorithms, right, where you use exponentially weighted history of the gradients as opposed to only relying on the current gradient, right? So this is what my current gradient is, but instead of only relying on the current gradient, I am looking at the history of the gradients, right? This is similar to what we have seen in the momentum-based gradient descent. And yeah, this is classical momentum. Then you do something known as bias correction. I'll just tell you the formula for now and not comment much on it as of now, right? So it's at time step t, once you have computed mt, then you compute the bias corrected value of mt, which is mt hat, which is just mt divided by 1 minus beta 1 raised to t. Then we have vt, which was the usual vt, which acted as a denominator for the effective learning rate. This is the same as what we had in RMSprop, right? So as I said, do everything that RMSprop does, plus just add this classical momentum term, right? That's what ADAM does. So again, you have a bias correction for Vt also. So you'll compute a Vt hat, which is Vt divided by 1 minus beta 2 raised to t, right? And then your update is Wt minus the effective learning rate into this moving average, right? As you have in momentum, which is the exponentially weighted average, right? So this is what the update equations for ADAM look like. And here this is looking at the L2 norm. What we mean by that is that if you have, or rather exponentially weighted average L2 norm, right? So you have V0 is simply delta W0 square, right? Because initially you don't have any other term, or rather 1 minus into 1 minus beta, right? And then if you look at Vt, it will have delta W0 square appropriately multiplied by some decay factor, then delta W1 square again multiplied by some decay factor, and all the way up to the current gradient, right, multiplied by 1 minus beta, right. So if I just ignore the decay factors and if I treat this as a collection of values as a vector, then what I'm looking at is the L2 norm of that vector, right. So that's what is the meaning here, and it's just not an L2 norm, it's an exponentially weighted L2 norm that you are taking, right. So that's what you need to remember. If you look at Vt, it has all the terms from delta W0 square all the way up to delta Wt square, and they are exponentially weighted, and you're taking the square. So that's the same as taking like an exponentially weighted L2 norm of a certain vector, right. So that's what I wanted to indicate here. And why am I saying that is something that will become clear, I think, a little bit later in the discussion. Okay. And typical values for beta 1 and beta 2 are beta 1 is 0.9 and beta 2 is 0.999. So since beta 2 is 0.999, so this 1 minus beta 2 is essentially a very small quantity, right? So you're taking a very small fraction of the current gradient. Okay. So now let's run ADAM and try to compare it with the other algorithms that we have. Yeah. So let me just see again. Yeah. So in this case, again, ADA delta reached the convergence fast, but ADAM is also reached faster than the other algorithms, and RMSprop as usual has the convergence problem, right? So this is not to show that, okay, Adam is always going to be better than all the other algorithms, but I'm just showing how Adam is behaving in this case, right? And there's a difference between Adam and Ada delta. Adam is more in the line of RMSprop with the momentum, whereas Ada delta also had this adaptive effective learning rate, whereas here you still have the initial learning rate, right? So you still have eta here, okay? Yeah, so you saw what happens there, and it seems to behave reasonably. Okay, so now I had mentioned that this Adam had this bias correction term, right? So the other concepts in the equations of Adam you already know, right? You already know what VT does. It kind of decays the learning rate. You also know what MT does, right? MT is the classical momentum term. The only new thing which has come up in Adam is this bias correction, right? Which is not clear to us why we are doing that bias correction, right? So let's see why we are doing that bias correction, right? So these are the update equations for Adam. So note that we are taking like a running average of MT, right? We are in MT, we are taking a running average of the gradients, right? So what do I mean by taking a running average of the gradients? Like I have the current gradient, I'm giving it some weightage, and I'm also accumulating the history. So the reason we are doing this is that we don't want to rely too much on the current gradient, right? Because you might get a sudden high gradient and then you might take a very large step, and you might don't want to rely too much on the current gradient. This is the same explanation as we have in momentum, where you want to keep looking at the history. If I'm constantly moving in a direction, then I want to keep some weightage for the history also, and then not make sudden movements based on just the current derivative, right? So that's why you have this exponentially weighted average, so that you have more weightage for the history, because history has accumulated over time, and less weightage for the current point in time gradient, right? So one way of looking at this is that you're actually, right, what you want in MT is that you want to look at the expected value of the gradient as opposed to this current value of the gradient, right? So instead of just looking at the current gradient, I would have ideally wanted to look at the expected value, right? So remember that our true gradient is actually a sum over all the data points that we have, right? But here we are going to do mini batch or some such version, and say we are doing stochastic in the worst case, right? We are just looking at one data point. Then I don't want to make decisions based on this one data point, but I would like to be closer to the mean of the gradients or the expected value of the gradients, right? And this exponentially weighted average is also trying to capture some kind of an average, right? Now the question is whether this exponentially weighted average is close to the expected value of the gradient, right? Because I'm taking a average, an exponentially moving average, is that close to the expected value? Because ideally I would wanted the expected value, because that would tell me over all the data points, if I had taken all of them, what would my gradient be, right? But I'm not able to take the expected value because there are a large number of data points, right? So what that means is, instead of expected value of the derivative, we are computing MT as some kind of an average, right? So expectation, you could think of expectation as the mean or the average, but instead of computing the true expectation, we are computing some MT, which is an exponentially moving average. Ideally, we would want that the expected value of MT is the same as the expected value of the derivative itself, of the gradient itself, right? This is what we would want ideally. Now let us see if that is really the case, right? Is that happening? If that's happening, then perhaps we don't need to do anything, right? So remember the momentum equations that we had, where we had ut is equal to beta ut minus 1 plus delta wt. Now and when we had expanded out those equations, you can go back and check those videos. We had written it as u0 is equal to delta w0, u1 is equal to beta times delta w0 plus delta w1, then u2 is equal to beta square times delta w0 plus beta times delta w1 plus delta w2, and so on, right? And this entire thing is essentially captured by this formula, right? So you can go back and look at those videos, but now I've in fact already explained it here itself, so you know what I am talking about. Okay. We now have, in Adam, we have a slight modification, that we have beta 1 and then 1 minus beta here, right? So here we only had the beta term. we only had the beta term here, but in Adam we have beta, and then this is also 1 minus beta, right? So we will arrive at a similar formula, but just note that this 1 minus beta is there. So let's see at what formula do we arrive at in the case of Adam. So we'll have mt is beta into mt minus 1. So this is the 1 minus beta. So m0 is 0, m1 is going to be this, m2 is going to be this. And again, if I substitute the value of, so what I did here is that I started off with, oh, can I move this or not? Yeah. Yeah. I started off with m0 equal to 0. Then my m1 was 1 minus beta times delta w1. m2 was beta into m1 plus 1 minus beta into delta w2. But then I've substituted the value of m1 as 1 minus beta into delta w1. And I'll keep doing this, right? So as I keep doing this, let's see where I reach. I'll again reach at some kind of a formula. And so m3 is going to be this, and if I expand it, I get this. And so now if I look at m3, it's actually 1 minus beta, the 1 minus beta factor I can take out, and it is time step 1 to 3, beta raised to t minus tau into the derivative at that time step, right? So that's exactly what is happening here. So I have the 1 minus beta term which I have taken out common. Then I have, for t equal to 1, I have beta square into derivative of delta 1, right? Then I have beta into derivative of delta w2, and then I just have delta w3, right? So for 3, this would be 3 minus 3, which would become 0. So the beta factor would disappear and you'll just have delta w3. For 2, it would be 3 minus 2. So beta raised to 3 minus 2, which is the same as beta, and then you will have the delta w2 here. So this is how the formula has been arrived at. So in general, for the tth time step, I am now ready to write the formula. So for the tth time step, the formula would just be 1 minus beta, a factor of 1 minus beta being common, right? And then beta raised to t minus tau delta w2. And it's very similar to this formula, except that you had this 1 minus beta term, which has shown up on this formula also, right? So nothing great here. Don't worry too much if you have not understood this right away. You can go back and look at the steps and you can derive this formula on your own, right? So I've derived the formula for MT, and this is important for the rest of the discussion that we'll have. Okay, so now let's look at, okay, now let's take the expectation on both sides, right? I have MT on one side and I have the delta WT quantity on the other side. So I'm going to take expectation on both sides. So expectation of MT is equal to the expected value of this expression. Now I'll just take the constants out and move the expectation inside. So the expectation, so 1 minus beta here will come out because it's a constant. Then I have the expectation of a sum, which is the same as the sum of an expectation, okay? And now again the beta term will come out and the expectation goes inside. And now what I'm going to assume is that all the WTs, they come from the same distribution, right? Because I have, what does that mean, right? So what does the distribution mean in this case? So you could think of right, the gradient itself could have different values, right? And those values could come from some distribution, right? So these are your derivative values on the x-axis, and you have a distribution. That means certain values here have a higher density as opposed to other values, right? And now at every time step, because your updates are changing and your weights are changing and you're moving along the loss surface, this distribution might be different, right? At some time steps, you might expect more smaller gradients. At some time steps, you might expect larger gradients. But we are making a simplifying assumption here that every time step, this distribution looks the same, right? So what does this distribution come from? Where does the randomness come from? So it comes from the data point that I'm picking up, right? I'm picking up random data points at every time step. So depending on the time data point that I have picked up, my derivatives might be different. And this is the distribution that I expect them to follow, right? And this distribution might change at different time steps, but I'm making this assumption that at all time steps, the distribution remains the same. That means the expected value at any time step is equal to the same, right? So I'm talking that expected value is the same for all the time steps. That's one simplifying assumption that I have made. And under that assumption now, let's see where we reach. So now we have made this assumption that all the derivatives were the same. So then we have this expected value of delta Wt. Now I can just, it does not depend on the time step t anymore, right? So I can take it outside the summation. So then I have 1 minus beta into expected value of delta W into that summation that I had. Now this summation looks familiar. It's a summation of a series, and this is beta raised to t minus 1 plus beta raised to t minus 2 all the way up to beta 0, and the sum of that series is just going to be 1 minus beta t divided by 1 minus beta raised to t divided by 1 minus beta, of course. So now I get this equation. So the expected value of mt is actually the expected value of the derivative into 1 minus beta t. So now if I had taken the expected value of mt by 1 minus beta t, then I would have got the expected value of the gradient, right? Hence I need this bias correction. I am just dividing the value of mt by this term 1 minus beta t, because if I do that, now this is actually my mt hat. So now what this is telling me is that the expected value of mt hat is the same as the expected value of the derivative, right? So that's what I am doing this bias correction, and you can have the similar derivation for the value of Vt also, right? So that's why we have to use bias correction in ADAM. So that's the main point of discussion when we are talking about ADAM, right? Why do you need a bias correction? All the other things in the equations are familiar. One is related to momentum, the other Vt is related to decaying, the learning rate in the denominator. And again, the Vt itself is an exponentially moving average, as we had justified in the case of RMSprop, right? So there are no other unknown or new concepts in the equation of ADAM, but this bias correction is the main new concept, which we have just understood why to do that. Okay, so now let's see what would happen if we don't do bias correction, right? So we'll again look at the equations, put in some values and try to see what happens, right? So this is the equation for Vt, okay? And now suppose delta W naught is equal to 0.1, okay? So now V naught is going to be beta 2 times 0, because Vt minus 1 was 0, and then 0.001 times 0.1 square, so it's going to be 0.0001, okay? And now eta t, the effective learning rate, is going to be 1 divided by the square root of this, which is going to be 316.22, right? So it already looks a very high learning rate to me, right? Now let's see what V2 would be. V2 would be 0.999 into V naught plus 0.01 into 0 square, and that would give me this quantity, okay? And that is again a reasonably high learning rate, right? So what we are seeing is that in the absence of bias correction, this is not bias corrected, right? I just took Vt, I did not take Vt hat, right? Please note that. So in the absence of bias correction, as the paper says, your initial steps could be very large because your initial learning rate would be very high. But now if I had done bias correction, okay, and I had the same situation, my W naught was 0.1. So now V naught is this, the bias corrected value is 0.01, okay, and now if I substitute this bias corrected value in eta, my effective learning rate is 10 as opposed to 316 here, right? Similarly, V2 gives me a certain value. If I bias corrected it, I get certain value, and now my learning rate is 13.8 as opposed to 316 here, right? So in the bias correction, when I'm doing bias correction, my initial learning rates are not becoming very high, right? So that's why you need bias correction to make sure that initially you're not doing some very rapid movements, because that could be faulty. And we'll see also through an example what happens, right? So let's look at this plot here. So here I'm going to compare what happens when you have ADAM with bias correction and ADAM without bias correction. And remember, our understanding is that if you don't use bias correction, the initial updates would be very high. That means the algorithm would move very fast, right? So let's see if that is happening. So notice that this blue curve corresponding to ADAM without bias correction would make very large initial updates. That's what we expect. So let's see if that is happening. And that is indeed the case, right? It has like gone very fast ahead and then it had to come back, right? It still converts probably easily in this example, right? Because this is a toy example and it had came back from the valley. But you could imagine situations where after making an initial update, it would enter some region of the loss surface from which a recovery might be difficult, right? It would have reached a region where in that region, whatever minima you could get would perhaps be much higher than what you could have got otherwise, right? So hence this initially the learning rate is very high in the case when you do not use bias correction, right? And that's what you're seeing here in these plots also. So let's understand these plots. So when we don't have bias correction, you see that your learning rates are higher, right? They are on this scale, you have values which are 2, 2.5 and so on. Whereas when you use bias correction, your learning rates initially are smaller. And then initially the learning rate was large. And then it starts decaying. And in the case of Badam with bias correction, so remember this brown or the red curve actually corresponds to the learning rate for W. And W was the direction which was sparse. So as it came close to the minima and it went into the valley, it still had to make some updates for W. So the learning rate was still increasing, which is what we would want, right? So this Adam with bias correction was able to adjust easier, whereas this guy had some initial very high learning rate and then it had to follow some trajectory. Of course, both of them converge. That is not a problem. But this is just to show that without bias correction, your initial learning rate could be very high. So I'll stop here with the discussion on Adam. And now we'll look at, in the next half an hour or so, we'll look at some variants of Adam, or maybe just one or two variants of Adam. Okay, thank you. So welcome back. And we were talking about Adam in the last lecture. And I would just like to say a few more things about the bias correction in Adam, which may again relate to things that we are going to do today. So I'll start with that and then I'll go to the next algorithm, which is going to be M.Khapra, right? So let's start with, let's just quickly talk about bias correction again, right? So one way of looking at what is happening in Adam is that, or in many of these gradient descent based algorithms is that, so you have these, on the x-axis, I have the number of iterations or epochs, right? And at every iteration, maybe from a batch or in a stochastic, from a mini batch or in a stochastic manner, I am computing the gradients, right? So let's say that, and there is some randomness in this, there is some noise in this because it depends on the batch that I have picked up, right? So now the batch is not, the mini batch is not a representation of the entire data. So depending on how good this mini batch is a representation of that entire data, the gradients that I compute from this mini batch may vary as compared to what I would have gotten from the full batch, right? So here what I'm trying to illustrate is that suppose I had computed the derivatives from the full batch, right? Suppose the red function here is what my true derivative function would have looked like from time step 0 to time step 100, right? But since I'm doing this mini batch version of the algorithms, I'm computing the derivatives from a smaller batch and hence I might get noisy estimates. So you can see that every time step, so this is the gradient that I computed at time step 0, this is at 1, this is at 2 and so on, right? So every point here corresponds to one time step, right? So it's 0 to 100, so there are 100 points here, right? Now, as you can see that it's like kind of varying, right? It's it's close to the true derivatives, but also there is some noise, right? You see some up and down movement there, right? And one way of dealing with this is to kind of say that instead of just relying on this gradient at this time step, I will take the average of all the gradients that I have taken so far, right? Or I would take the moving average of all the gradients. So instead of just relying on this point, so for example, this should be clear, right? Suppose instead of relying on this value here alone, let me just use a different color. If I take like an average of things which fall in this window, right? And this is the same as saying that, I mean, an exponential average is almost similar like to taking an average in a small window, because anyways outside this window your beta powers are so small that those points won't have much value, right? So you are kind of re-estimating the average. In the case of MT, you are writing it as beta into MT minus 1 plus 1 minus beta into the current derivative, right? So the current derivative is this one blue point that you have, and instead of relying on that blue point, you're also taking an exponentially weighted average of the history. So this is your way of kind of accounting for the fact that the current batch could be noisy. So hence let me look at the history also and kind of re-estimate this point, right? Now if you don't do bias correction, so now what I'm going to do is that for every black point, I am going to compute the new value of that black point using this equation. That means I'm going to compute this weighted history, right? So at time step 40, I have 39 blue points below it, and I'm going to take the value of each of those 39 blue points, and I'll say that beta raised to 39 into the value at time step or beta raised to 40, I guess, right? Maybe 39 or 40, whatever that power comes to, into the value at time step 0, right? Then beta raised to 38 into the value of time step t1 all the way up to 1 minus beta into the value at this t40th time step, right? So my new value is going to be this exponentially weighted average, right? That's what I'm going to do. So let's see if I plot that. So now for each of these blue points, I could compute the new exponentially weighted value, and then I can plot that, right? So let me see what happens if I plot that. So this is what happens if I plot that without the bias correction, right? So what happens is that I get, you can see that my black curve now is a bit farther away from the red curve, at least during the initial time steps, right? And yesterday also we had seen that during initial time steps we have a problem when we use bias correction. So why does that happen? Let's try to understand that. So our formula is beta into mt minus 1 plus 1 minus beta into the current time step value, right? So that's it, delta Wt, right? Now at time step 0, my delta Wt was around 1, right? But my beta is 0.999 and this is 1 minus beta. So this is going to be 0.001, right? And my mt minus 1 is 0 because I initialize at like, so mt minus 1, since t is equal to 0, this is going to be m minus 1 and that I have initialized to 0, right? So this whole sum moves towards 0. It becomes very small and then the same thing keeps repeating, right? Because in the next time step again, now at time step 1, again my value was around say 0.8, right? So then I have 1 minus beta into 0.8, right? And plus beta into my history so far, which was around say 0.001, right? And now again this 1 minus beta is a very small value. So that's why it will stay towards close to 0 and it will take a while to then start coming close to the true values, because after a while, now this is your history and all these initial parts are getting very small weightage and these new guys are getting higher weightage. So then slowly it kind of gets rid of its history because of the large power of beta, right? And then it starts relying more on the recent guys and those recent guys are all farther away from 0. So then it also starts coming close to the true curve, right? So that's why what happens if you don't use bias correction. Now the same thing, if I had used bias correction, this is what will happen, right? So now if I use bias correction, then it gets divided by that 1 minus beta factor and then I don't have a problem, right? So in particular what happens, right? So I'll show you. So my m0 is minus 1, okay, and my mt is going to be beta into, oh, sorry, mz, sorry, what am I saying? M minus 1 is 0 because I initialize it as 0. My history is initialized as 0, then plus 1 minus beta into mt. Now at time step 0, my value is 0.5, right? So this, so this value is 0.5 and this term is going to disappear, right? So I'll get 1 minus beta into 0.5. That's what my mt is going to be. Okay, today the pen is not working well. That's what my mt is going to be, and my m hat t, which is the bias corrected guy, is going to be mt divided by 1 minus beta raised to 1 in this case. And so now these two betas will cancel and I get 0.5 and hence my approximation is close to the true value. And now it stays like that, right? Because it does not have this weight of 0 pulling it down, right? Earlier it started off at 0, then it got stuck there and it took a while to get the shape of the function, but now it has started from the right point and it's now closer to the function, right? So that's what happens in the case of exponentially moving average, and that's why we use this bias correction in the case of Adam. Okay, so we are done with this. So I had skipped this part yesterday. Now the rest of the stuff for Adam we have already done. We already did this. We looked at multiple explanations for why the initial updates are going to be larger, right? So we saw these derivations, then we saw this plot, all of that is done, right?